Hello everyone, this is DSS Zindabad and today we are going to discuss the daily challenge of Leetcode. The problem is house robber. Let's jump into the problem statement. You are a professional robber planning to rob houses along the street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security system connected and it will automatically contact the police if two adjacent houses were broken into the same night. Given an integer array num representing the amount of money of each house, return the maximum amount of money you can rob tonight without alerting the police. Okay, so from this problem statement, I understand the first thing that I need to do is I cannot rob two adjacent houses. Okay, so you cannot rob two adjacent houses. And the second thing is I need to find the maximum amount of money I can rob. So let us assume that I have been given something like an array nums, right? And that is 1, 2, 3, 1. Okay. So this array here is representing the money each house has. Okay. And as a robber, I need to rob them in such a manner that at any point of time, I am not robbing two adjacent houses, and eventually after robbing, I have the maximum amount with me. So when we talk about adjacent, it means that if you look at zeroth index, just right next to it would be the index which is adjacent to it, right? When you talk about the index that is 2, right? So it has two adjacent, the zeroth index and the third index. So that means if I am choosing that I will be robbing second index, right? That means I'll be robbing the first index which has amount 2. That means I cannot rob whatever is on the index 0 or 2 because they're just adjacent to it, right? Then if I am robbing whatever is present on index 1, I have to rob something that is on index 3. I hope it is clear that what is adjacent. Now let's talk about the approach. Okay, so what approach can I have? First, let's understand the different ways in which I can rob these houses, right? So I had something like this nums, which is 1, 2, 3, 1. Okay. And my end goal is to have maximum money and while not robbing two adjacent houses. Okay. So what I'll say is let's try figuring out all the possible ways I can do it. Okay. So first I'll say let's begin by robbing the last house. As soon as I've robbed the last house, let's have something like say sum. So it has 1 that I have earned 1 money after robbing the third house. As the second index is just adjacent to third, so I cannot rob this. I can rob the next one, right? So, I mean, I can rob from any one of these. So, I am choosing that I'll rob whatever is present on the first index. So, I'll add 2, right? As soon as 2 is added, that means again, my first index is also has been robbed. I cannot rob the 0th index. So, this is one way. The other way I can do this is that suppose I say I'll not be robbing the third house. Instead, I'll be robbing the second house. So, now my sum has something like 3. As I have robbed 2 and obviously we're going to go in one direction only, right? I cannot rob 1 now. So what I can do is I can rob the 0th house. So that gives me 4. The above one was giving me 3. And similarly, there can be a method wherein I say that, okay, I can start from the first house. So if I do that, I'll have something like 2. And as I have robbed the second house, I cannot rob the second, I have robbed the first house, which had 2 money in it, right? So I cannot rob the second house, the second number house, right? So because it is just adjacent to my index 1, I can rob the third index house, right? So it gives me 3. So here I can see there can be other ways, right? But considering these ways also, I can understand that my maximum possible answer would always turn out to be 4. So when we see this, we understand that I'm trying to figure out all of the possible ways, right? so that I can rob and get maximum money without robbing two adjacent houses. So when we talk about all possible ways, we know what we have to apply. We have to apply recursion. So what recursion says is that you handle the base case, rest is something I'll figure out. So basically, whenever we talk about recursion, as we know that we have to figure out three things. First one being the base case, right? The base case has the edge cases and the termination point that we'll be having, right? So the edge cases and the termination point. Second thing, I have to explore all the possibilities. So here in this basic problem statement, as I want that the amount, see, as a robber, I would want to get as much money as I can, right? So I need to maximize the amount. So maximum is what I need to do. And third is building the recursive function. Okay. So let's quickly again make this array so that we can discuss how we'll be forming and performing these three steps. Okay, so let's quickly make this array and let's see how we'll be performing these three steps on it. Okay, so I had nums something as 1, 2, 3, 1. Okay, so we'll come to the base case later. First, let's talk about the recursive function. Okay, so here in the above, I saw that I can start from any index when I'm going forward, right? But for the time being, let us assume that you are either starting from the 0th index or the 3rd index, so that it is easier. We do not have to handle two cases where it's like you have to handle both the adjacent. It is better to go in one direction. So I'm saying let's either start from the last house or the first house in the street wherever I am. Okay. So I say, okay, in this case, I'll be starting from my last index, that is 3. So that is like, okay. Now, what I see is that if at any point of time, I have two options. Being a robber, I have two options. That means I can either rob the house or I can skip the house. Okay. So robbing the house means I am taking it. I am taking the money of that house, and skipping it is I am not taking it. So it is a very direct concept of take not take, right, in recursion. So I am saying that let us have something like take and not take. So at any point of time, if I am taking this, I have to add its value because this nums array is denoting the money that is stashed in each house, right? So nums of I plus C. Now I was on the 3rd index. As I know, the 2nd index is just adjacent to it. So that means I cannot go here, but I can go to its next index. So I say that if you are taking it, next recursion call would be made for I minus 2. That means we cannot go to the next house. Why? Because you just looted its adjacent house. If you loot its adjacent house again, the police will be alerted and we don't want that. The other case can be not take. In this, I am not taking anything. So that means my profit from that house is 0. And as I have not considered whatever was on the 3rd index, I can take the 2nd one. So I'll say, okay, recursion, figure out to me that will I get the maximum profit if I am ignoring the one index I'm standing on and going to the next one and looting. Okay. And talking about exploring all possibilities, we can simply compute the maximum of both take and not take. Now, let's talk about a very little condition that we need to take care of when we are handling take. Suppose you are standing on the 1st index, right? So when you are standing on the 1st index, you can see that your I becomes equal to 1. So if a take call is made, you can see that we'll have something like 1 minus 2, which is minus 1. And that is not possible. We'll get a runtime error. So here we can have simply an if condition that if I is greater than 1, only then you can take it. And as we have to figure out the maximum, so we can initialize take with something like a very minimum value, minus 1e9 or something. Okay. So now let's talk about the base case. Talking about the base case, as I told you that my starting point is the last index. That means the last house on that street, right? So when will I stop? I'll stop as soon as I get the last house. I've reached the last house, right? So I'll say that at any point of time, if my I has become 0, in that point of time, you just return me whatever is the value there. Considering these recursive calls, I need to handle that at any point of time, if I becomes less than 0, right? That means my index has become less than 0 to prevent any runtime error. I can simply return a very small value like 1e9. Why I'm using 1e9, not int max, int min? I mean, we cannot obviously use int max because then we have to find maximum and we'll get that as the answer, and that would be wrong. I mean, why cannot we use something like int min is because int min generally leads to integer overflow if there's subtraction or addition, right? So I prefer using this. So this is how the recursive code would be made. Let's quickly code this up and then we'll talk about its time complexity and how we can optimize it. Okay, so this is the code. As discussed, what I'll do is I'll quickly create a solve function here, right? I'll say int solve. And let's discuss its parameters. See, as I know, I just have a 1D vector. So I'll just need one pointer to move over it, right? So I can have something like index, and I will also have this vector here, right? So I'll say just simply return me the solve function. I'll pass the index as I was we can even start either way. You can start from the 0th house, but I am starting from the last house. That is what I feel is more convenient for me, right? And I've made this call that you are starting from the last house and you have this num. Okay. So now what happens is I say, first of all, we'll have the base case, right? We'll write that later. Then we'll have the recursive function. So as I know that for any particular house, I have two choices. That is, I can either take it or not take it. So initially, I can only take it when the I is greater than 1. Because we saw we do not want to go into the minus indexes, which will lead to a runtime error. So I'll initialize it with something like a very small value, 1e9. And I'll say that if index is greater than 1, that means there is one more house, right? In that case, what you do is you will say take is equals to whatever is present in the current house, you take it. And for robbing the next house, you have to go to the next. So that will be index minus 2 because we are going from right to left, right? And nums is passed as it is. For not take, it is simple, right? We say that if you're not taking that particular house you're standing on, for example, if you're standing on the second index and you're not taking it, it is okay, take 0. And then you can even rob, if you want to, the house right next to it. So it will be index minus 1 nums, right? And then we'll return whatever is the maximum of take and not take. So here it's done. Now, talking about the edge case first, we'll have something like that if at any point of time where index becomes less than 0, right? Because we are decrementing it in our recursive calls, right? So in that case, you return something that's a very small value, or we can have, right? You can return something that's a very small value. Talking about the base case, I'll say that if at any point of time my index becomes equal to 0, so in that case, you simply return me whatever is present at that index. That means the 0th index. I think we're good to go. Let's run it once. And we're getting the right answer. I'll not be submitting it because we'll get a TLE. I'll quickly copy paste this code so that we can discuss its time complexity and further optimizations. Okay, so this is the code that we just wrote, right? Before moving into its time complexity, space complexity, and its optimization, let's have a quick dry run that how is this solving our problem. So suppose we had the nums array, we've been starting. That is 1, 2, 3, 1, right? So what I said is I'll be creating the recursion stack space as well as the recursion tree for you to understand how visually it is happening, for you to have a better understanding. Okay. So initially I have a solve function and I am passing here as n is 4. So n minus 1, that is 3, is passed. So I come to the solve function, and in my recursion stack space here, right, I have added S3 call here, and my pointer is pointing towards it. As soon as I come to the solve, I see is index less than 0. It says no, neither is the base case being satisfied. I go to the take condition. So I say keep take as something like 1e9, and I'll check that is index greater than 1. It will say yes, index is greater than 1. So I'll say okay, then change take to something like whatever is present on num index. Index here is 3. So num index 3 has 1. 1 plus have a solve function call for index minus 2. As index was 3, 3 minus 2 is 1, right? And now S1 is added into my recursion stack space, and my pointer is pointing here. As soon as I come to S1 function, I check that E is the base case or the edge case being satisfied. No. Then I go to the take condition. I'll say that if index is greater than 1, it will say no, it is not greater than 1. So I'll be like, okay, that means I cannot go into this condition. So here for this, I have a take of minus 1e9. So now I'll go for not take. That means I'll not be taking this. If I am not taking this, then I'll say make another call, that is 0 plus call the solve function and have index minus 1. Index here is 1. So 1 minus 1 is 0. Okay. So S0 function is added into my recursive stack space, and I am here, right? As soon as I go to S0 function, I see that yes, now it is satisfying my base case. So as it is satisfying my base case, what I have to do is I have to return whatever is present on nums 0. So I see on nums 0, I get a 1. So I get a 1 here. So it returns a 1. And now as I had to compute the maximum in this, right? Sorry. So it is returning a 1 here, right? As it is returning a 1, it has done its work. It has lived its life. So S0 gets popped out from my recursion stack space. My pointer is again pointing to S1 function. Now when it is pointing to S1 function, it says that I have exhausted both of these and I have reached the return statement. I need to return whatever is the maximum of the take, and this was the not take, right? So we see the maximum of minus 1e9 and 1 is 1. So it says, okay, I'll return a 1. Okay, as soon as it returns a 1, it gets popped out from my recursion stack space, and my pointer goes to the S3 function. As soon as I'm on the S3 function, I see that I have completed my code till here. I need to work on this line segment, right? So I have to work on this line segment. So it says, okay, now what you need to do is you will be considering the not take case. So this was the take case for S3 function, and you'll be working with the not take case. So what it says is, it says that you do not take it to 0 plus have a call for solve function wherein you decrease the index by 1. Here you can see the index is 3. So it is decremented by 1, it becomes 2, right? And S2 is added into my recursion stack space, and now my pointer is pointing towards S2. As soon as I come to S2, I see that neither the edge case nor the base case is handling it. So I'll have a take here, which is initially minus 1e9, and I'll say is the index greater than 1. I'll say yes, 2 is greater than 1. So that means I can update take to whatever is present on num index. Index was 2. So nums 2 had 3. So we'll have 3 plus we'll call a solve function, and that solve function says index minus 2. That means 2 minus 2 is 0. And S0 function is added into my recursion stack space, right? And now my pointer is pointing towards that function. As soon as I come to S0, I see it is satisfying the base case. I return whatever is present on num0. And on num0, I have got a 1. So I have 1 here. S0 gets popped out, right? And now it is giving the value as 4 to its parent function. Then S2 says, now my pointer is again pointing to S2, right? And it is saying that I have worked till here. Now I have to figure out this part of the code. So it goes for the not take call. Okay. So for the not take call, it says have something like 0 plus solve index minus 1. Index was 2. So it is 1. S1 is added into the stack, right? As soon as it is added into the stack, my pointer is pointing towards S1. So S1 says I am not satisfying either the base case or the edge case. So you have to figure out the take and the not take case for me. So here I have further two cases, that is take and not take. So for take, initially it is 1E9, it has been initialized with 1E9. But as I see that index, which was 1 this time, it is not greater than 1, which is required for me to update take. So take remains minus 1E9. And my not take goes for 0 plus solve index minus 1, index was 1, 1 minus 1 makes it 0. And now S0 is added on top of my stack, right? And now my pointer is pointing towards here. So S0 says that, yeah, I am satisfying the base case, return whatever is present on the index 0 of nums. It says 1. So 0 plus 1 returns a 1, right? As soon as it returns, it gets popped out from the stack. Now my pointer is again pointing towards S1 function in my recursion stack space, right? And it says that you have to find the maximum of minus 1E9 and 1. So it says that is 1, and you'll return that to your parent function and will pop out from the stack. Now my pointer is pointing towards the S2 function in the recursion stack space. And the S2 says that from one side I'm getting a 4, from the other side I'm getting a 1. I have to return a maximum, so it will return 4 to its parent, that is S3, and it will pop out. Now I'm on S3. I have from the take side I have 1 as the answer, and from the not take side I have the 4 as the answer. So as in the case of maximum, I'll return a 4 and I'll pop out from the stack. So this is the dry run for the recursive code we wrote. So what observations do we find here? The first one being that for every element in the nums array, I see that I have two choices. That is, I can either take it or I can not take it, right? And then that further gets extended, right? So it makes a time complexity of O2 raised to the power n, because we have got two choices and we have a space complexity of O of n. We have this space complexity because of the recursion stack space that is being maintained. So in the worst case scenario, almost all the elements will be added into the recursion stack space. Okay. So this time complexity is something that will not be accepted and you will need to optimize it further. Now for optimization, we can see a pattern here in the recursion tree that we have just drawn, that I am recomputing things. Here I have figured out S0. Again, S0 is being figured out here. Here S0 is figured out. Then S1 function is being recomputed. Again, here it is being recomputed, right? And similarly, here we had a nums array of size 4. If we would have a nums array that is even more greater in size, we have even more overlapping subproblems, right? So we see we have overlapping subproblems. So as we have the overlapping subproblems, I know what I can do is to optimize this kind of a problem, I use something like dynamic programming. So what does dynamic programming do? It says whatever you have computed, save it at a place and just do not recompute it. If you're again having a function call for the same thing, just pick it up from where you have saved it and use it directly rather than recomputing all of it, right? So when we talk about dynamic programming, there are subtle changes that will be made to the existing problem and it shall work. So basically, this was the code. So see, this was the code that we were working on, right? We have to just make little changes whenever we are working with TP, right? One of the approaches is the top-down approach, which is known as memoization. So in memoization, what do we do is we have a DP vector, right? And the DP vector size is equal to the number of parameters that are changing in my function, in the recursive function, right? So here the recursive function is solved and I can see only one parameter is changing, that is index. So I'll have a DP vector of 1, right? That means DP vector, 1D DP vector I'll be having, right? And its size would be similar to what is the size of the nums vector. So considering that the number of elements were n in nums, similarly it will have a size of n. And then moving further, we can initialize it with -1. -1 here represents that none. Okay, so -1 here represents that it has not been computed yet. Okay. So what I'll do is, now rather than recomputing everything over and over, I can simply store it in my DP vector, right? So I'll quickly show you how it's done. That it has been not computed, that it has not been computed yet. So basically, I'll create a vector here. That's a 1D DP vector, right? And I'll pass it here. I'll add it into the function. And here, before having these computations of take not take, I'll simply have this condition that if DP of whatever index you are on, that is not equal to -1. That means it has been computed. Then you return DP index, right? We'll add DP in these recursion calls here. And whatever you were figuring out for each index at every point of time, you just store it in the DP index now, so that you do not have to recompute it. After we have done these subtle changes, the time complexity boils down to O of n, that is linear, and the space complexity also boils down to O of n. Here we have O of n plus O of n. That is because one, we have a DP vector, and second, we'll be having the recursion stack space. So what I'll do is the dry run I just showed you, I'll be using that similar dry run, and I'll show you how it becomes faster. So as we knew that what we had was nums 1, 2, 3, 1 as the array that was given to us, right? And here, let us assume that I've added all these things. Okay, so what I'll do is I'll quickly make this little changes in my code, then I'll copy paste the code and do a quick dry run for the same. So guys, this was the recursive code that we just wrote, which had a time complexity that was exponential in nature. And we discussed that we can have something like memoization, which will help us boil down the time complexity to linear. So I can initialize my DP. I'll add it into my recursive function here, right? Let's quickly add it to the function. And here, before we are having the recursive work, that means we're figuring out again, I'll say if DP of index is not equal to -1. In that case, you just return me whatever is the DP of index. And for the take function also, we'll pass DP for the recursive call, and here also we'll pass DP. And then we'll return DP index. That means for every index which is being computed, you just store it in the DP vector. I think we're good to go. Okay, yeah, there needs to be a little space here. And see it's working fine, right? Now I'll quickly copy paste it, and then we can talk about its time and space complexity. So this is the memoization DP code that we just did, right? And as I told you, its time complexity is linear and its space complexity is O of n plus O of n. That again makes it O of n. Now we'll quickly have a dry run for the same and see how we're getting it. So we had a nums array that was 1, 2, 3, 1 that we have discussed earlier, right? So I'll be drawing the recursion tree as well as the recursion stack space. Here we have the DP vector that is of the similar size as nums. So it has 4 elements in it, and all of them are initialized to -1. So what happens is, first call is made here. I get S, n was 4, so n minus 1 makes it 3. And in my recursion stack space here, S3 is added, right? And my pointer is pointing towards it. I come here, I see none of these cases is being satisfied. So I know that for this call, I have two choices. I can either take this house, or I'll not drop this house and I'll go to the next one. So if I take it, it is initially -1E9, and I'll check is the index greater than 1. I'll say yes, 3 is greater than 1. So you can update take, and you can have something like nums index. From the third index, I get a 1 plus have a call a solve function that is index -2. So 3 minus 2 makes it 1. Now S1 is added into my recursion stack space, and my pointer is pointing towards it. As soon as I come here, I now know that S1 has two choices. That is, you can either take it or not take it. So for take it, it is initially -1E9, but as I see that the index is no more greater than 1, so the take remains as it is. We cannot update it. So we go to the not take case. Here I'll go for 0 plus call the solve function. When you're calling the solve function, that will be index -1. Here you can see index was 1, so 1 minus 1 makes it 0. So S0 is added into my recursion stack space, and my pointer is pointing towards it. So as soon as you go to S0, you see that the index has become 0. So you simply return whatever is present on the index 0. So that is 1. So you get 0 plus 1, you get a 1 here, right? And you will simply return this value as 1 to your parent. So as you return it, you will pop out the function that has been completed. And now again, your pointer is pointing towards S1 function in the recursion stack space. So here it says that I've exhausted the computation that I had to do. Now put whatever is in the DP index. So index now here is 1, if you see. So here as the index is 1, I'll say put ever what is the maximum. So whenever you put the maximum, you see that 1 is maximum. So for the first index in DP, you put a 1, right? So I see that I've completed whatever I had to in the case of S1 function, so it also gets popped out. Then I go to and it is returning back to its parent function, that is S3. That will be 1 plus 1, that makes it 2. It is returning a 2 to S3. Now what happens is, I am on the S3 function. My pointer is pointing towards the S3 function, right? And now we'll be figuring out the not take case. So it has 0 plus solve index -1, that is 2. So now 2 will have two cases, that is take and not take. So now, because it is not satisfying any of the other conditions and it has not been pre-computed, so my take is initialized to -E9, and I'll say as the index is greater than 1, so I can update it and it will have nums of index. Nums of index, that means nums at index 2 we have a 3. 3 plus have a solve function for index -2, that is 0. So for S0, as I know it's a base case, I'll return num 0. So I'll directly get from this call, I'll return 1. So 3 plus 1 becomes 4, and it is returned to its parent. So as we know that we had this function called S0, it has returned 4 to its parent, that was S2. It gets popped out, and now my recursion stack space pointer is pointing to S2. So S2 says you figured out the take case, go for the not take case. When you go for the not take case, we get something like 0 plus solve. Index -1 here is now 1, right? As soon as I go to S1 now, what I can do is I can see that it has been computed in my DP. It is not -1, it is 1. So I do not have to recompute all of it. I do not have to have another function call. I can, from here, I'll pick the value and I'll put it here. So 0 plus 1 makes it 1, and I'll simply return 1. Then I'll pop this out. I am on the S2, as I have to take the maximum. I'll take 4, and 4 gets popped out. Function S2 gets popped out, and we're again on S3. S3 takes the maximum, that is 4. See here, as you just saw that only at one place we could fill in the position because we had a little array. If we were having something like a big array, then a lot of recomputations are saved. And because of this DP array, we get a time complexity which is linear in nature. Talking about the space complexity, We have O of n because we are using a DP vector which is of size n, which is similar to the number of elements which are present in my nums array. And we have O of n another, that is for the recursion stack space. So a question comes to our mind that can we further optimize it? So the answer is yes. If, see, I cannot make it better in terms of time complexity. I have brought it down hugely from something which was exponential to a linear time complexity. And I cannot remove the DT vector so off now. But I think I can change, I can like eliminate this recursion stack, right? So I can eliminate this recursion stack space. How I can do is I can do that using the method of tabulation. So tabulation is a bottom-up approach. In this, what we do is we simply say that whatever was the base case here, you start building it and forming a tabulized iterative solution. Okay. Here, the time complexity is O of n and the space complexity is also O of n because we'll just be having a DT vector. We'll not be having any extra recursion stack space. Okay. So let's quickly code this up and then we'll move forward to the best optimized solution. So guys, this was the solution for memoization. I'll be using the similar solution and just two quick changes to it. So basically, you can derive a bottom-up approach from the top down being memoization, bottom-up being tabulation. So here I'll have a DP vector and I'll initialize it with 0. Now see, you have to just follow it in the same order. As you can see that I am saying that at any point of time, if my index is 0, I need to return num 0. So I'll say that DP of 0 is equals to nums of 0. Just store this, right? Then I'll run a for loop as I've handled the index 0. I'll run a for loop from 1 till n, right? And I'll say that, see, int take again remains like we'll initialize it with a very minimum value. And I'll say that if I is greater than 1, in that case, it is just similar to the recursion code you have written, right up here. So I'm saying if I is greater than 1, take nums of I plus, here we were calling the solve function. Now, as we have converted the recursive function into a iterative function, I'll have dp I minus 2, right? And for int not take, I'll have just a call that is dp I minus 1. We can have 0 plus dp I minus 1. You write 0 not, it does not matter, right? And then what I can do is I can say that at every point of time for every I, dp of I, that index, we're storing the maximum of take, comma, not take, and then eventually return me whatever is on the index. See, because see, here when we were doing this memoization solution, there we were having a recursion call from n minus 1, right? So we were going from the top. Now here we are starting from the bottom, right? So I'll be returning the dp n minus 1 as the answer. Let's run it. I think we're good to go. It's working fine. Let's submit it. Okay. So here what you have to do is that if you are taking it, then let's quickly add it here. So guys, it is very important for you to understand that how you can have debugging skills because that is of utmost importance. If you get an error, how you solve it, right? We'll quickly run it again for this case here. Let's see, is it working fine? Because it is really important for your internships and your interviews. It is working fine. Let's submit it. And it is accepted. Now, I told you that what we can do is we can further optimize it. Now, how can we further optimize it? See, you see something that at every point, what I want is, I want to know the previous, right? I mean, if I'm trying to figure out the take case, I want to know twice the previous. That means previous, right? Previous post of previous, right? And if I am not considering it, I just want to know the previous. That did I take it or did I not take it? The conditions like that, right? So what I'll do is I'll say let's have a space complexity of O of 1. We cannot reduce the time complexity further, but we can reduce the space complexity. As here in the tabulation code, I still have a space complexity of O of n because of the dp vector. So I'll quickly comment this all out. Now what I am saying is, I'll be like, okay, let's use the pointer approaches, right? So I'll say that let's handle a little of base cases, that if n is 0, then you have to return 0, right? Or if n is equal to 1, in that case, you return whatever is nums of 0, because there's only one house and that's the maximum profit as a robber you can get. Let's have a previous 2, which is nums of 0. Basically, what is it representing? It is representing dp of I minus 2. That means I want to know the previous status, right? And then we'll have a previous, which will be nums of, which will be the maximum of nums of 0, comma, nums of 1, right? And that is basically representing dp of I minus 1. We just used them in the previous tabulation solution. I'm doing nothing new. I'm just converting the forms and just trying to space optimize it from a vector to a two-pointer approach. Now, as you see, I've handled the 0 and the first case here in line 34 and 35. I'll have a for loop that's running from I is equals to 2 till I is less than n, I plus plus, right? And I'm saying int take, it is equals to nums of I, whatever is present on the ith index of my nums, that's the amount that I have to loot, and previous 2. Why? Because previous 2 was what, like previous, right? And int not take is equals to previous. Then what I'll say is, I'll say we'll have now a current that will be storing the maximum of take and not take, right? And after that, I'll just quickly change the values. I'll say that whatever previous had, now previous 2, you need to have it. And whatever the current had right now, it has whatever it has computed right now, previous you need to have it. And we'll simply return the previous. I think we're good to go. Let's quickly run it once. It's working fine. Let's submit it. And it is working fine. So for this code, the two-pointer approach, we have a time complexity of O of n and a space complexity of O of 1. So guys, here we saw 4 approaches. The first one was recursion, right? In the recursive solution, as we had 2 choices, that was we can either loot the house, that means take the money from the house, or not take the money from the house. We had a time complexity which was big O to the power n and space complexity of O of n because of the recursion stack space. We optimized it further to memoization, right? In the case of memoization, I was using a dp vector, right, plus recursion. So here, what I did was my time complexity boiled down to O of n, and my space complexity became O of n plus O of n, which is again O of n, representing the dt vector and the recursion stack space. I further improvised my code by moving into tabulation, right? Here, I used the dp vector and the iterative method to solve it. And my time complexity became O of n and space complexity became O of n because I'm just using a dp vector. I do not have any recursion stack space associated. I further optimized my space complexity using space optimization approach, wherein I utilized 2 pointers, right? The 2-pointer approach. and I got a time complexity that was again linear and a space complexity of O of 1. Thank you so much for viewing the video till the end. If you have any comments, any discussions, you can always comment in the section and we can discuss it. Thank you so much. Please like, share and subscribe.